For centuries, electricity and magnetism were treated as two completely separate forces of nature. To the scientists of the time, they had no shared connection. Magnetism was defined by lodestones, natural rocks that could attract iron, and when suspended, always pointed north. Sailors used these stones to navigate across oceans, long before anyone could explain why they worked. Electricity was seen differently. It was the sudden spark of a static shock, or the steady, weak flow produced by early chemical batteries, like the voltaic pile. This divide lasted until 1820, when Danish scientist Hans Christian Ørsted noticed a detail that had been overlooked for centuries. During an experiment, he placed a compass near a wire. The moment an electric current flowed through that wire, the compass needle suddenly twitched. That tiny movement was the first evidence of a hidden link. It proved that a wire carrying a current generates its own magnetic field, revealing that this electrical energy could be used to exert a real physical push on the world around it. However, the magnetic force from a single straight wire is incredibly weak. It is enough to nudge a light needle, but not nearly enough to move heavy mechanical parts. To increase the force, you have to change the shape. Bending the wire into a loop concentrates the magnetic field directly through the center. By wrapping the wire into many loops, you create a solenoid. Each loop reinforces the field of the next, which multiplies the strength of the magnetism along the central axis of the coil. The force becomes even stronger if you add an iron core. The coil's field forces millions of tiny magnetic domains inside the iron to snap into alignment, focusing the power of the magnet. This is an electromagnet. Unlike a natural magnet, its power is controllable. You can turn this magnetic force on or off simply by connecting or disconnecting the current. With a magnetic force that was now both powerful and controllable, the stage was set to turn that invisible push into continuous motion. To build a motor, you place this electromagnet, the rotor, between two permanent magnets. When the power is on, the magnetic fields interact. One side of the coil is pushed away, while the other is pulled forward, which creates the torque that spins the rotor. But the motion doesn't last. After half a turn, the opposite magnetic poles align, the pulling force disappears, and the motor locks into place. This happens because magnets naturally seek a state of equilibrium. Once the north and south poles find their match, they have no reason to keep moving. For a motor to spin forever, it has to find a way to prevent the magnets from ever reaching that resting state. The solution is a mechanical switch called a commutator. It consists of a segmented copper ring that spins with the coil and two stationary metal brushes that deliver the electricity. Electricity flows from the brushes into the segments, charging the coil and starting the rotation. Right as the rotor is about to reach that locked state of equilibrium, the spinning segments cross the gap to the opposite brushes. This instantly reverses the direction of the current flowing through the coil. Because the current direction changed, the magnetic poles of the electromagnet also flip. The side that was being pulled toward the permanent magnet is suddenly pushed away. This creates a repeating cycle. Current flows, torque is generated, and the commutator flips the poles just before the motion can stop. A DC motor is essentially a machine designed to trick magnets into falling toward a balance they are never allowed to reach. While this model is simple, the physics scale from small toy motors to the massive machines that drive our technology. Engineers used this core principle to build industrial-sized motors using massive iron cores and heavy-duty coils to power the machinery of the modern world. This design eventually led to specialized variations: induction motors that run without brushes, stepper motors for precise digital movement, and high-efficiency brushless motors. Even though these modern designs are highly complex, they all rely on that same invisible interaction Ørsted discovered with a single wire and a compass. Much of the rotational motion we see today, from the fans cooling our electronics to the wheels of an electric train, is the result of this mechanical trick. It all depends on our ability to keep those magnetic poles chasing a balance they will never catch.